All right, so just some last things to talk about here. You're going to have to learn to not only determine the equilibrium constant K from concentration values that you provided, but you're going to have to manipulate that equilibrium constant K based on things that you do with the original equation. So if you reverse the equation, you must invert the equilibrium constant. So as we look at that first equation there on the left of your screen, the equilibrium constant for that forward reaction would be products over reactants, or C times D over A times B. But if we reverse it, we get A times B, which are now our products, over C times D, because we've reversed the reaction. Therefore, if we want to figure out what the rate constant is for the reverse reaction, all we have to do is take 1 over the equilibrium constant of the forward reaction. 2. If you multiply the coefficients in the equation by a factor, you raise the equilibrium constant to the same factor. So as you look at the equilibrium expression on the left of your screen, if we were to write an equilibrium constant for that, we would get products over reactants. If we were to do the same for the equilibrium expression on the right, notice there we've multiplied our equation by a factor of 2, which can be simplified as seen on your screen there. Essentially then, all you have to do with your original equilibrium constant value is raise it to the constant of the same factor, in this case 2. And the third manipulation you're going to have to do is sometimes you'll be asked to add 2 or more individual chemical equations to obtain some overall equation. Simply multiply the corresponding equilibrium constants by each other to obtain the overall equilibrium constant. So, reaction 1 on your left, there's our equilibrium constant expression, products over reactants. Reaction 2 on your right, there's our equilibrium constant expression for us. Now let's say we wanted to add those 2 equations together to give us A forms C. Recognize here that if I were to write an equilibrium constant expression for that, it'd be products over reactants C over A, but that's the same as the product of those initial equilibrium constants. Notice here that the concentration of B sort of cancel out. So ultimately, all you need to do here, if you're ever adding 2 individual chemical equations together, is simply multiply their equilibrium constants. Okay, and then the last thing for today is you need to recognize that the equilibrium constant K, although oftentimes we'll be talking in terms of concentration, you can describe it in terms of pressures, especially for gaseous reactions. So the concentrations of a gas are proportional to their partial pressures, therefore the equilibrium constant can be expressed in terms of those partial pressures. Notice that we can use Kc as the equilibrium constant with respect to concentrations. Notice the brackets there for concentrations. However, if we're going to talk about the pressures of some gaseous reactants or products, you will see it expressed the exact same way. It's still products over reactants, except now we're talking about their respective partial pressures. Notice K sub P. However, since the partial pressure of a gas in atmospheres is not the same as the concentration in molarity, the value of Kp for a reaction is not necessarily equal to the value of Kc. Your relationship between Kp and Kc is provided to you on your screen in your notes there. This formula you need to memorize. So commit it to memory. We're not going to take the time here to talk about how that relationship is derived, although there's some really great work in your textbook if you have a dying passion to figure out how we've come to this understanding as the relationship between the two. But just recognize right now that's what it is there. Again, keep in mind we're going to be using the 0.0821 R value because we're talking about gases here, and that is going to be for gases with pressures in atmospheres, temperature in Kelvin, and then delta N is going to be our change in number of moles. Quick test tip here, though, is to keep in mind that Kc will equal Kp. It can happen, it will happen, but that is only true when the change in the numbers of moles of gas products compared to gas reactants is 0. And that is true because when you raise that then to the 0 power, it's essentially 1, and therefore Kp will be equal to Kc. But again, important, that is only true when the change number of moles is